Right now, a golden record is drifting through the darkness between the stars. It carries the sound of a mother's first words to her child, the cry of a humpback whale, rain falling on a summer afternoon, and a piece of music composed by a man who died 250 years ago. It has been traveling for nearly 50 years and has covered only a fraction of the distance to the nearest star. Somewhere out there, in the cold silence of interstellar space, a civilization might one day hold it in whatever they use for hands. They will see where we live. They will know we exist. And then the universe will show them something that physics has never once bent for anyone, the wall that says, "You cannot come." If this journey is doing something to the quiet part of your mind, I hope you will like this video and subscribe. It means the world to us who created this. So sit tight and comfortably. Close your eyes. In 3, 2, 1, liftoff. There is an object moving through the space between the stars right now, at this exact moment, as you read these words and breathe and feel the quiet weight of wherever you are settled. It has been moving continuously since the summer of 1977. It has not stopped, not slowed in any meaningful sense, not turned around, not powered down its trajectory. It burns no fuel today. It carries no active engine. It is simply falling at extraordinary speed through an ocean so vast that the word ocean is a comforting lie we tell ourselves to make the scale feel manageable, falling outward from the star that made it possible in the direction of a darkness that has no bottom. Its name is Voyager 1, and it is the most distant human-made object in the history of our species, and nothing we have ever built has come close to it, and nothing we are currently building will surpass it for longer than most civilizations have existed. It is traveling at approximately 17 kilometers per second relative to the Sun. That is roughly 38,000 miles per hour. It sounds fast. In human terms, it is extraordinarily fast. It is more than 45 times faster than a rifle bullet, fast enough that it could circle the Earth at the equator in just over 18 minutes, fast enough that even a single day of travel at that speed covers about 1.4 million kilometers. By the time you finish reading this sentence, Voyager 1 has moved another kilometer deeper into interstellar space, and none of it is fast enough. That contradiction that something moving at 38,000 miles per hour can be, in the context of the universe it is traveling through, essentially standing still, is where this story begins. Because Voyager 1 is not just a spacecraft. It is a mirror. It reflects back at us, with uncomfortable clarity, the precise scale of what we are dealing with when we talk about space, about distance, about the possibility of reaching anyone or being reached by anyone. It reflects back the physics of the problem in a way that is not theoretical or abstract. It is literal, it is measured, and it is humbling in a way that takes a while to fully settle. But before we get to the physics, and before we get to the question of what happens when someone finds what Voyager 1 is carrying, we have to understand what Voyager 1 actually is, where it came from, what it has done, and what it is doing right now. Because the spacecraft is not just a vehicle, it is a story. Voyager 1 was launched on September 5th, 1977, from Cape Canaveral, Florida. It was not the first of the two Voyager spacecraft to leave Earth. Its twin, Voyager 2, had launched 16 days earlier on August 20th, but it was built to travel a faster trajectory, and it overtook Voyager 2 not long after launch. The mission was designed to take advantage of a rare orbital alignment of the outer planets, one that occurs only once approximately every 175 years, an alignment that allowed a spacecraft to use the gravity of each planet it passed to slingshot itself outward toward the next, gaining speed, essentially for free, by borrowing kinetic energy from the motion of the planets themselves. This technique is called a gravity assist, and it is the reason that Voyager 1 has reached the distances it has, because no rocket we have ever built could have launched it into interstellar space using fuel alone. The solar system itself provided the final push. Voyager 1's primary mission was the outer planets, and it executed that mission with a precision that still inspires awe. It swept past Jupiter in March of 1979, and what it showed us there permanently changed our understanding of the solar system. The Great Red Spot turned out to be a storm that had been raging for centuries. Jupiter's moon Io was found to be the most volcanically active body in the solar system, with massive sulfur plumes erupting in real time as the cameras watched. Nobody had known Io was volcanic before Voyager 1 arrived. It was a discovery that arrived completely without precedent, from a world we had observed for centuries through telescopes and never really seen at all. The thin rings around Jupiter, nobody knew they existed. Voyager 1 found them. Then Saturn, November of 1980, and the images that came back were something that people working at JPL at the time have described as entering a room and having the ceiling suddenly lift away. The ring system, seen from close enough to see the individual ringlets and their gaps and their shadow patterns and their braided structures, was not what anyone had modeled. The rings had been predicted to be smooth and simple, organized by gravity into clean bands. Instead, they were intricate beyond imagination, with thousands of individual ringlets and structures that moved in ways that took years to fully explain. The moon Titan, shrouded in orange haze, turned out to have an atmosphere thicker than Earth's, with nitrogen as its primary component, a chemistry that some scientists immediately noted had uncomfortable similarities to what Earth might have looked like before life began. After Saturn, Voyager 1 had completed its assigned work. There were no more planned planetary encounters. The next objects in its trajectory were not planets but the open interstellar medium, and nothing waiting to be photographed in the way Jupiter and Saturn had waited. Some people at JPL expected the mission to effectively end. Instead, something else happened. The scientists and engineers decided to keep listening, and Voyager 1 kept talking. The instruments kept running, the data kept coming home, and for decades, as the spacecraft climbed outward beyond the orbit of Uranus, then Neptune, then Pluto, then the Kuiper Belt, then the region where even the outer reaches of the solar system begin to thin into something else, the signal kept arriving on Earth. In 1990, Carl Sagan persuaded NASA to command Voyager 1 to turn its camera backward toward the inner solar system one last time before the cameras were powered down permanently to save energy. The image that resulted is one of the most famous photographs in the history of science. It showed Earth as a pale blue dot, less than a single pixel in size, suspended in a ray of scattered sunlight against the blackness of space. From a distance of roughly 6 billion kilometers, the entire world, every mountain and ocean and city and person who had ever lived, was a speck so small and faint that it was barely distinguishable from noise. Sagan wrote about that image in words that have been repeated so many times that they have become almost part of the scientific canon. But the image itself retains its power, because it is not metaphor, it is not illustration, it is a real photograph of where we actually are. After the cameras were shut down, Voyager 1 continued outward. The instrument packages measuring plasma, cosmic rays, magnetic fields, particle densities, continued operating. Scientists were particularly interested in what would happen when the spacecraft reached the heliopause. The heliosphere is the bubble of space dominated by the sun's influence, the region where the solar wind, that constant outflow of charged particles from the sun, maintains its pressure against the surrounding interstellar medium. Like a boat creating a bow wave in water, the sun moving through the interstellar medium creates a bubble, and everything inside that bubble is within the sun's direct sphere of influence in terms of particle environment. The boundary where the solar wind gives way to the interstellar medium is the heliopause, and for decades, scientists wondered what crossing it would actually look like in the data. In August of 2012, Voyager 1 crossed the heliopause. It was not a single dramatic moment. The crossing took months of analysis before the team was confident enough to announce it, because the boundary is not a clean line, but a gradual transition zone. But by the autumn of 2012, the data was unambiguous. The environment around Voyager 1 had changed in the ways scientists had predicted. It would change when the spacecraft left the solar wind bubble and entered the true interstellar medium. The density of ions from the sun dropped. The intensity of interstellar cosmic rays increased. The magnetic field orientation shifted. Voyager 1 was in interstellar space. It was, officially and observationally, the first human-made object to leave the heliosphere, the first physical piece of humanity to exist in the space between the stars. Voyager 2 made the same crossing in November of 2018 from a different direction, which turned out to be scientifically valuable because the two spacecraft crossed the heliopause at different angles, and the comparison of their readings helped scientists understand the shape and structure of the heliosphere in 3 dimensions. As of the spring of 2026, Voyager 1 is approximately 25.4 billion kilometers from Earth. Voyager 2 is approximately 21.35 billion kilometers out. These numbers are so large that they require some translation to become meaningful. One way to feel them, a radio signal traveling at the speed of light, takes more than 23 hours one way to cross the distance between Earth and Voyager 1. More than 23 hours for light, the fastest thing in the universe, the thing that circles the Earth 7 times in a single second to make one leg of the journey. The team at JPL sends a command. 23 hours pass. The command arrives. Another 23 hours pass. Any response comes home. Every single interaction with Voyager 1 is a commitment of nearly 2 full days. By November of 2026, that one-way signal time is projected to reach 24 hours, 1 full light day, making Voyager 1 the first spacecraft to sit at a distance of 1 light day from Earth. The spacecraft is aging in ways that are difficult to watch if you have spent any time understanding how much of ourselves is invested in its continuation. The power comes from 3 radioisotope thermoelectric generators, essentially canisters of radioactive plutonium that generate electricity as the plutonium decays. At launch, they produced roughly 470 watts. Decades of radioactive decay later, they now produce barely enough electricity to run a few household light bulbs. That declining power has forced the mission team to make increasingly painful choices about which instruments to keep alive. In March of 2025, the low-energy charged particles instrument was shut off on Voyager 2. In April of 2026, The same instrument was deactivated on Voyager 1 to buy the mission additional time. Voyager 1 now carries just two functioning science instruments. One that listens for plasma wave emissions in the interstellar medium, and one that measures magnetic fields. Engineers believe this power-saving measure may extend the mission's scientific life by roughly 1 more year. Eventually, and the team knows this, and speaks about it in the particular language of people who have given decades to something they know is ending. Eventually, the last instrument will go quiet. The last signal will arrive at the antennas of the deep space network on Earth. And then Voyager 1 will continue on in absolute silence, a mute ghost moving at 38,000 miles per hour through the dark between the stars, carrying something it was never designed to carry. But that turns out, in retrospect, to be the most important thing on board. The golden record. It sits bolted to the outside of the spacecraft body. It is a 12-inch disc of gold-plated copper, roughly 30 centimeters in diameter, housed in an aluminum protective jacket. It has a stylus, a needle included in the jacket, and on the cover of the jacket there are diagrams etched in the metal itself, in binary notation, using the hyperfine transition of hydrogen as a universal measurement standard, explaining how to play the record, what rotation speed to use, and how to decode the encoded images. The choice of hydrogen as the reference unit was deliberate and elegant. Hydrogen is the most abundant element in the universe. Its hyperfine transition produces a radio signal at a frequency of approximately 1.42 gigahertz that is detectable across cosmic distances, and any civilization sophisticated enough to operate in interstellar space would almost certainly have encountered this signal and understood it. It was the closest thing Carl Sagan's team could devise to a truly universal unit of measurement, a clock tick built not from human convention but from atomic physics. The idea for including a record on the Voyager spacecraft came from Frank Drake, the astrophysicist who had developed the famous equation bearing his name for estimating the probability of intelligent civilizations in the galaxy. Drake pointed out that a phonograph record is a mechanical medium. The information is not stored electrically or magnetically, but physically, carved into the grooves of the disc as variations in depth and width that a needle can read. This means the information does not require any active power source to preserve. It does not decay the way electronic storage decays. It does not corrupt the way magnetic media corrupts. In the cold vacuum of interstellar space, where temperatures hover around -455 degrees Fahrenheit and radiation can degrade many materials, but does not corrode gold-plated copper in the same way it corrodes organic compounds, a properly protected record could survive for an extraordinary span of time. Drake estimated 1 billion years. Some estimates have been more conservative, placing the upper limit of legible preservation at a few 100 million years. Even the conservative estimates represent a duration so far beyond human civilization that the comparison becomes meaningless. Our entire recorded history is roughly 5,000 years. The most pessimistic estimate for the record's preservation is 40,000 times longer than that. The contents of the record were assembled by a committee chaired by Carl Sagan at Cornell University, working over a period of nearly a year, with the understanding that what they were choosing would be, in all probability, the last and only portrait of humanity ever to leave the solar system in physical form during the lifetimes of everyone involved. The weight of that responsibility is visible in the choices they made. They were not choosing a greatest hits compilation. They were choosing what to say about a species to an audience they could not see, in a language they could not assume would be understood, across distances they knew made the whole exercise almost certainly futile. They chose 116 images, encoded as analog waveforms, essentially the same principle as old cathode ray television, where a beam sweeps across a screen line by line, and the brightness at each point is recorded as a variation in signal amplitude. The images begin with calibration material, mathematical diagrams that allow the decoder to verify their method is working before proceeding to the actual content. Then comes the solar system, the sun, the planets, their relative sizes and distances. Then Earth, the continents, the atmosphere, the oceans, the weather patterns seen from space. Then life, cells, DNA, the structure of chromosomes, the stages of human development from fertilized egg to birth to childhood to adult. Then humanity in its environment, people eating, people running, people in cities, people in markets, people by the sea, people holding hands, mothers nursing infants, children laughing, a supermarket with its aisles of abundance, airplanes, highways at night, glittering with moving lights, mathematical equations, a page of music, the structure of a musical instrument, images that tried, in the space of 116 frames, to answer the question, what is this species? The audio was assembled with equal care. It opens with greetings in 55 human languages, ranging from the ancient Akkadian, one of the oldest written languages in human history, Sumerian, Su-mer-i-an, even older, to modern Mandarin, modern Hindi, modern English. The greetings vary in tone and content. Some are formal and diplomatic. Some are warm and personal. 1. In a language whose civilization has since transformed beyond recognition, simply says, "We are happy here, and you be happy there." There is something in that one that is different from the others, something less concerned with the weight of the moment, and more concerned with the simple wish that wherever you are well. Then come the sounds of Earth that the committee decided an alien civilization should hear. Rain falling, wind, thunder, surf breaking on a shore, crickets, frogs, birds. The songs of humpback whales, and this choice was not accidental. The humpback whale was, in 1977, one of the most threatened species on the planet, still being hunted commercially by several nations. Its population, a fraction of what it had once been. Including the whale song was partly a scientific choice because whale vocalizations are genuinely complex acoustic structures that encode information in ways we still do not fully understand, and they demonstrate that intelligence and communication are not uniquely human properties on this planet. It was also partly a political statement, made in metal, launched into space. There are other minds here, and we are in the process of destroying them, and we want you to know they existed. Then, footsteps, a heartbeat, laughter, a mother speaking her first words to a newborn child, a sound so specific and so universal within our species that it sits on the record as something that does not require translation, only recognition, and yet might be the most alien sound on the entire disk to any civilization that is not mammalian, not social in the way we are social, not born in the way we are born. The music spans 27 selections from cultures and centuries as different as it was possible to make them. There is Johann Sebastian Bach's Brandenburg Concerto No. 2 chosen because of its mathematical precision and its layered complexity. There is a Javanese gamelan piece whose tonal system is built on scales entirely different from Western music, using intervals that sound strange to ears trained on European harmony. There is a Senegalese percussion piece. There is a Peruvian panpipe melody. There is Chuck Berry's Johnny B. Good, which reportedly caused some debate among the committee, with several members wondering whether it was wise to tell any potential listeners that teenagers had been a feature of our civilization. There is Louis Armstrong playing melancholy blues. There is a piece of Azerbaijani folk music, Azerbaijani, and a Georgian chorus, and a Navajo night chant, and the Queen of the Night aria from Mozart's The Magic Flute, and a string quartet by Beethoven, and a piece of music from Papua New Guinea, and a song by the Bulgarian State Television Female Vocal Choir, whose harmonics sound like they are coming from somewhere outside ordinary human experience. The selections are not ranked. They are not arranged by importance. They are arranged to show range, to demonstrate that this species makes music, that it makes many kinds of music, that music is not a single thing on this planet, but an infinity of things, and that all of them are real. And then, tucked between the music and the natural sounds, there is something else, something that Carl Sagan described as perhaps the most personal element of the entire record. Andrew Yan, who was serving as the creative director of the project and who had recently, secretly, fallen in love with Sagan, they had confessed their feelings to each other just days before the recording session, sat quietly in a meditative state, and allowed her brainwaves to be recorded using an electroencephalogram for 1 hour. The recording was encoded onto the record. She was thinking, she later said, about the history of Earth, about the development of civilization, about the great dreams and the great failures of the human species, about what it means to be alive in the universe, and about falling in love. All of that, the electrical signals of a human brain processing the whole weight of existence, is encoded on the disk, and no one on Earth knows how to decode it, and no one who might find it in the dark will have any idea what it is, and it is on the record regardless, because she and Sagan and the rest of the committee decided that if they were going to send a portrait of humanity into eternity, it should contain the interior of a human mind at its most alive. The record also contains a message from President Jimmy Carter, written and included at the time of launch, which reads in part, "This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours." Those words are more precisely calibrated than they might appear. They do not claim greatness. They do not assert that we deserve contact. They say we are small. They say we are distant. They acknowledge the attempt to survive the uncertainty, the fragility, and they reach toward a future that is explicitly not ours, a time they call yours, meaning whoever reads this, whenever they read it, wherever they are. There is one more element on the cover of the record jacket, and it is perhaps the most consequential of all for the particular story we are telling here. It is a map. Specifically, it is a pulsar map, a diagram showing 14 pulsars arranged relative to a central point that represents the Sun, with their periods encoded in binary notation, using the hydrogen hyperfine transition as the base time unit. A pulsar is a rapidly rotating neutron star, the collapsed remnant of a massive star that ended its life in a supernova that emits a focused beam of radio waves as it spins, creating a signal that pulses with extraordinary regularity. Each pulsar has its own characteristic period, its own fingerprint, as precise and distinctive as an atomic clock. The periods of these 14 pulsars, combined with their angular positions as seen from the Sun, uniquely locate our solar system in the galaxy. Any civilization with the radio astronomy to have catalog pulsars, and any civilization advanced enough to be operating in interstellar space would have done so, could in principle triangulate our position from the map. We told them where to find us. This decision was debated, and it was made deliberately. Carl Sagan and his colleagues were aware that some people considered it unwise that broadcasting our location to unknown intelligences carried risk, since we know nothing about what those intelligences might want. Sagan's view, which the committee ultimately accepted, was threefold. First, any civilization technically capable of finding the record in interstellar space was almost certainly already capable of detecting us through other means, because our radio and television transmissions have been expanding outward from Earth at the speed of light since the early 20th century, filling a sphere roughly 100 light-years across with our signals, and any civilization within that sphere with sensitive enough instruments might already know we exist. Hiding our address on the record would have been futile as well as rude. Second, the kind of civilization sophisticated enough to operate in interstellar space and to decode a record would, Sagan argued, likely be old enough and advanced enough that simplistic territorial aggression would not be their primary mode of interaction with the universe. Third, and most simply, the alternative was to say nothing, and that felt, to the people making the record, like the wrong choice at the level of basic moral principle. If you are going to reach out at all, you reach out honestly, so the map is there. Our address is etched in gold-plated copper, drifting through the interstellar medium at 38,000 miles per hour, attached to a spacecraft the size of a compact car. And it will be there, long after the last instrument has gone dark, and the last signal has arrived, and the last engineer who worked on the mission has lived out a full life and died. The record does not need power. The record does not need a transmitter. The record is the message, and the message will outlast everything else about the mission. In approximately 40,000 years, Voyager 1 will make its closest approach to any star, the red dwarf Gliese 445, currently located in the constellation Camelopardalis, which is an M-type star of roughly 60% the Sun's mass, roughly 1/10 the Sun's luminosity, currently about 17.6 light-years from the Sun. Voyager 1 will pass within about 1.6 light-years of this star. 1.6 light-years is still an immense distance, roughly 9.5 trillion miles, but it is the closest any human-made object will come to another star for at least that long. In 40,000 years, every human language currently spoken will be as transformed from its current form as modern English is transformed from the grunts of our pre-linguistic ancestors. Every civilization currently operating on Earth will have been replaced, reorganized, or forgotten multiple times over. The last ice age ended 12,000 years ago. Written history is 5,000 years old. 40,000 years is 8 times the span of everything we know as recorded human civilization, and Voyager 1 will still be moving. When scientists shut down the last instrument, when the final signal comes home and is logged and the receivers are pointed elsewhere, when the mission is officially over and the team disbands and the offices are repurposed for other projects, Voyager 1 will not stop. It will not slow. It will keep moving at 38,000 miles per hour, through the dark, through the cold, through the nothing, carrying its golden disk with the sounds of rain and whales and children and the brainwaves of a woman in love, carrying our address, carrying the musical selections of 45 dead composers and musicians, and the living ones who had no idea their music was going to space, carrying the structure of DNA and the orbit of the planets, and the image of a mother speaking to a newborn child, carrying all of that into a silence so complete that no human being will ever hear it again. And then, somewhere in that silence, somewhere in the 40,000 or 40 million or 400 million years of drifting that lies ahead, the question arrives. The question that sits at the center of everything that follows. The question that turns the golden record from a beautiful object into a genuinely haunting one. If they found it, the record, the spacecraft, the address, the map, what would they actually do? Not as poetry, not as speculation about alien consciousness. What would the physics allow? What happens next requires us to understand, first, what it would take for any civilization to even hold that disk. Because the odds of finding something in this small, in a space this large, are so vanishingly small that they deserve their own examination before we can begin imagining the scene. The interstellar medium is not nothing. That is an important place to start, because the popular image of space as a perfect vacuum is not quite accurate, and understanding what actually fills the space between the stars matters for understanding the scale of the challenge. Between the stars, the dominant material is hydrogen and helium gas at densities of approximately 1 atom per cubic centimeter. In some denser regions, molecular clouds, stellar nurseries, the density climbs higher. In the most rarefied stretches of the void, it drops lower, but as an average, 1 atom per cubic centimeter. This sounds like more than nothing until you compare it to anything else. The best laboratory vacuums that human technology can currently produce contain approximately 10 million molecules per cubic centimeter, meaning our best artificial vacuum is 10 million times denser than interstellar space. The air you are breathing right now, as you read this, contains approximately 2.7 times 10 to the 19th power molecules per cubic centimeter. The interstellar medium, at 1 atom per cubic centimeter, is less than 100 millionth the density of the air inside a vacuum flask. It is, by any standard available to human experience, nearly perfect emptiness. And through this near-perfect emptiness, Voyager 1 is drifting at 38,000 miles per hour, occupying a volume of space roughly equivalent to a moderately large refrigerator. Now, consider what it means to find that refrigerator. The volume of the interstellar medium in the vicinity of the solar system within, say, a sphere of 50 light-years in every direction. A region that contains only a few hundred stars is a number that requires scientific notation to express comfortably. 50 light-years translates to roughly 473 trillion kilometers. The volume of a sphere with that radius is approximately 4 divided by 3 times pi times that radius cubed, a number in the range of 4.4 times 10 to the 38th power cubic meters. Voyager 1 occupies a volume of perhaps a few cubic meters at most, including its antenna and extended booms. The fraction of that sphere that Voyager 1 occupies is a number so close to zero that it cannot be meaningfully expressed in ordinary decimal notation. Writing out the zeros would take longer than the spacecraft has been in flight. The practical implication is this: the probability of any civilization accidentally encountering Voyager 1 by random chance, even if they are actively moving through the region of the galaxy that contains it, is not merely small. It is not merely negligible. It is so close to zero that it would take a number of civilizations larger than the estimated number of stars in the observable universe, each individually searching the interstellar medium for random objects, for any single one of them to stumble upon it by accident in the next several billion years. This is not an exaggeration. The math genuinely returns answers of this magnitude. Voyager 1 is also, at this point, essentially invisible. During its operational phase, it emits a radio signal on the order of 22 watts, roughly the brightness of a dim household light bulb, transmitted across the interstellar medium. For human receivers equipped with the enormous dish antennas of the Deep Space Network, that signal is detectable from here because we know exactly where to point. But from an external vantage point, from some other star system, a 22-watt radio transmitter at interstellar distances would be buried in noise, undetectable against the radio background of the galaxy with any instrument that has been proposed in current technology. And once the mission ends and the transmitter goes dark, Voyager 1 will emit nothing at all. No light, no radio, no heat signature worth detecting. It will be, to any external observer, a mote of metal in an ocean of darkness, as invisible as a single grain of sand resting at the bottom of the Pacific Ocean would be to someone looking down from the International Space Station. So, for any alien civilization to find Voyager 1, the scenario requires something other than chance. It requires either a level of technological capability so far beyond ours that they can detect any physical object of significant density anywhere in their stellar neighborhood, perhaps through some form of gravitational wave sensing at resolutions we cannot currently imagine, or through some method entirely outside our current scientific framework. Or it requires that the civilization already knows roughly where to look, because they have already detected us through other means and have been studying our solar system with enough resolution to spot the spacecraft. Or it requires that Voyager 1 drifts into the direct vicinity of an inhabited star system over geological timescales through the slow geometry of galactic motion. None of these possibilities is impossible. The third is, in fact, mathematically guaranteed to happen eventually, in the long enough run, because the galaxy is not infinitely large, and Voyager 1 will eventually pass through stellar neighborhoods over millions of years of drift. And if the galaxy still contains inhabited star systems at that point, some small fraction of passes will bring it close to one. But eventually, in this context, may mean tens of millions of years. It may mean hundreds of millions of years. Let us set aside probability for a moment and assume the finding happens. Let us say that a civilization has Voyager 1 in its possession. We do not need to specify how. We need only to say, it has happened. And now, we need to understand what happens in the moments, or the years, or the decades after that, because the process of recognizing what the object is, understanding its purpose, and decoding its contents, is itself a fascinating exercise in what we can actually know about another civilization's capacity for interpretation. The first thing they would notice is what the spacecraft is not. It is not a natural object. Natural objects in the interstellar medium are gases, dust grains, comets, asteroids, and occasionally rogue planets, objects produced by stellar formation and evolution and ejected through gravitational interactions over billions of years. They are made primarily of silicate rock, ice, carbon compounds, metallic iron. Voyager 1 is made of machined aluminum, titanium, copper, gold, platinum, and complex polymer insulation materials assembled in geometric configurations that do not occur in nature. The angles are too regular. The surfaces are too smooth. The composition is too precisely controlled. Any civilization with enough chemistry to analyze the spacecraft would immediately understand that it was manufactured by something, somewhere, at some point in the past. That recognition is the beginning. Once they know it is artificial, they know they are holding a message. The next step, and this is where the extraordinary foresight of the record's designers becomes apparent, is that the message is designed to be self-explanatory at the most fundamental level. The cover of the record jacket is not just decoration, it is a technical manual. It uses binary notation, the simplest possible mathematical system, as its language, and it anchors that language in the hyperfine transition of hydrogen, the most recognizable and universal physical phenomenon available. The hyperfine transition occurs when the electron in a hydrogen atom flips its spin relative to the proton in the nucleus, releasing a photon at a frequency of approximately 1.42 GHz with a corresponding wavelength of approximately 21 centimeters. This transition produces the most intensely studied and catalogued radio signal in the universe. Any civilization capable of radio astronomy would have encountered it. Any civilization capable of building a spacecraft would have measured it. It is, in the fullest sense of the phrase, a universal reference point. The cover diagram uses this transition as a clock tick. It tells them the rotation speed of the record in terms of hydrogen transitions per revolution, a measurement that, once understood, gives them everything they need to know about playback speed. It shows them the geometry of the stylus and the groove. It shows them a sample of the first image encoded on the record, decoded correctly, so they can verify their interpretation before committing to the full process. It is, in its structure, an act of extraordinary pedagogical patience, a set of instructions written for an audience the writers could not see, in a language the writers could not assume, using only the shared currency of physical law. If the civilization that finds the record has sophisticated mathematics and physics, and any civilization capable of existing in interstellar space would almost certainly have both, then working through the cover diagram is a solvable problem. It might take time. It might require multiple generations of scientists, or the equivalent of scientists, working through the puzzle collaboratively. But it is solvable, because it is built on physics that does not depend on culture, or biology, or shared history. It is built on the structure of hydrogen and the properties of sound waves and the geometry of a circular groove, and these things are the same everywhere in the universe where hydrogen exists and sound can propagate, which is everywhere. Assuming they decode it, and we are, for the purpose of this exploration, assuming they do, because otherwise the record is simply a decorative object, and our story ends there. What do they encounter? They encounter the 116 images first, because the sample image on the cover primes them for visual decoding. They see the calibration grid. They see the mathematical diagrams. They see the solar system, a star, and 9 orbital paths, with the relative sizes of the bodies encoded in a way that can be compared to the star to give absolute scale. They know, immediately, that the object came from the third planet of that system. They see Earth blue, partially cloud-covered, recognizably a water world, and they can immediately begin estimating the composition of the atmosphere from what they know about the electromagnetic properties of the surface they are looking at, because that is the kind of inference any civilization with spectroscopy can make. They see life. The images of cells and DNA tell them that this species uses a molecular information storage system based on long-chain polymers, which is interesting because it is one of the most chemically elegant solutions to the heredity problem, and they may have encountered it before, or they may be encountering it for the first time, and either possibility changes how they interpret what they are seeing. They see humans. This is perhaps the most loaded moment in the entire decoding process. The images of human beings, the silhouettes that show our bipedal form, our relative sizes, the proportions of our limbs and heads, the ways we move and eat and hold each other, reveal an enormous amount about our biology. They can estimate our size relative to the objects around us. They can see that we are bilateral, symmetric, terrestrial, warm-blooded in the way the images suggest, social in the way the images show. They see a mother with a newborn child, and they understand from the context alone that this species has extended parental care, that the young are born helpless and require years of adult protection. This is not true of all biological life. It is a specific evolutionary strategy with specific implications for social structure, for cognitive development, for the length of childhood, and the investment in learning. Any civilization doing xenobiology, the study of life from other worlds, would find this detail significant. They hear the sounds. The sounds are on the audio portion of the record, which plays after the images. The natural sounds of Earth are, in many ways, the most alien section of the record to any civilization that did not evolve on Earth. The sound of rain requires an atmosphere with liquid water precipitation. This immediately confirms atmospheric composition beyond what visual analysis could alone determine. The sound of thunder requires a specific kind of electrical discharge in a dense atmosphere. The crickets and frogs and birds confirm the biodiversity of the planet, many independent lineages of complex life, which means life has been evolving on this world long enough to have diversified dramatically, which means the planet is old and has been consistently hospitable to life for a very long time. The humpback whale songs are the most complex sounds on the record, and they would likely stop whatever passes for listening dead in its tracks. Whale songs are long, structured, culturally transmitted acoustic performances that change over time within populations and spread between populations across ocean basins. They are not simple calls. They are elaborate compositions that unfold over hours, with recurring themes and variations and apparent intentionality of structure. Any civilization with a concept of music would recognize something in them that goes beyond simple animal signaling, and would immediately understand that this planet was producing acoustic complexity before the beings who built the spacecraft arrived, and then the music begins. 27 selections, spanning 5,000 years of human history and every inhabited continent on Earth. The first thing they would notice, and this is genuinely interesting, is the mathematics. Music, at its most fundamental level, is organized vibration, and vibration follows mathematical relationships that do not depend on biology or culture. The octave, the relationship where one frequency is exactly double another, occurs because our auditory systems evolved to recognize the similarity between a sound and its first harmonic, but the mathematical relationship itself is universal. The fifth, the relationship of 3 to 2 between frequencies, produces a consonance that, in the physics of resonating strings and columns of air, reinforces itself rather than interfering with itself, which is why so many musical traditions across such different cultures arrived at the same interval independently. Any civilization that produces organized sound, not necessarily music in our sense, but structured acoustic information of any kind, would recognize mathematical patterns in human music, even if the emotional content was entirely opaque. What they would make of the emotional content is genuinely unknowable. Music carries emotional information for human listeners through a complex interaction of evolved biological responses, cultural conditioning, and learned association. A minor key sounds melancholy to people raised in the Western European musical tradition, partly because of physics. The intervals create more acoustic beating and dissonance, and partly because of cultural association built up over centuries of musical practice in which minor keys were used for sad contexts. To a civilization with no such cultural history, the minor key is simply a set of frequency ratios, and the melancholy is invisible. Whether they would construct any emotional meaning from the music is something we cannot predict. But they would almost certainly recognize that the music was not random, that it was organized according to principles that reflect intentionality and structure, and that the incredible diversity of musical styles across the 27 selections implies a species with a rich and varied cultural history stretching back a long time. Then the brainwaves. Andrew Yan's electroencephalogram occupies a section of the audio track that, without context, would seem like abstract data, which it is, in a sense. A brain's electrical activity, recorded from scalp electrodes, is a noisy, multi-channel signal that requires significant processing, even for human neuroscientists to interpret. Without knowing what it is, a decoding civilization might struggle to categorize it. It does not fit the pattern of music. It does not fit the pattern of speech. It does not fit the pattern of natural sound. It is something else. Whether they would ever understand it, whether they would ever know that they were holding, in whatever they use for storage media, 1 hour of a human mind's interior life, the electrical signature of a person thinking about love while traveling through geological history, is something we cannot say, but it is there. And then, at some point in the decoding process, they find the pulsar map, 14 lines radiating from a central point, with frequencies encoded in binary notation. They check the frequencies against their own pulsar catalog. They find 13 matches. Pulsars shift in period over time, and 14,000 years of travel might have changed the periods slightly, or they might be measuring from a different angle, and the apparent positions might have shifted, but 13 is enough. They triangulate. They find the star, third planet, water world, complex biosphere, one intelligent species that has been broadcasting into space for over a century, if they are close enough for those signals to have reached them yet. They know where we are. They know what we are. They know what we sound like, and what we look like, and what we value enough to put on a golden disc and launch into the dark. They know we have children, and whales, and music, and a mathematical understanding of the universe, and at least one person who fell in love and thought it was worth recording. Now what? This is the question that the entire first part of this story has been building toward, and the answer requires us to look not at what the civilization wants, but at what the universe permits. Because wanting and permitting are very different things, and the universe has never once bent its rules for anything that wanted them bent. The physics that governs the answer is the same physics that built the stars. The civilization lives near. The same physics that made the record possible. The same physics that keeps Voyager 1 moving at 38,000 miles per hour through the dark. And that physics is about to say something that it has never said differently to anyone, not to us. Not to any hypothetical alien civilization reading a golden disc, not to any mind anywhere in the observable universe. The wall, it says, is real. And the wall is not made of engineering problems. It is made of the deepest structure of physical law. And the question of whether any civilization, however advanced, can find a path through it, that is what we must examine next. The wall is not made of metal. It is not a barrier that exists in space the way a door exists in a hallway. You cannot point a telescope at it and see it. You cannot touch it or measure its thickness or look for a gap somewhere along its edge. The wall is made of equations, and specifically of the accumulated, interlocking, mutually reinforcing consequences of a small number of physical laws that happen to govern every object with mass that has ever tried to move fast through this universe. These laws do not have exceptions. They have never had exceptions. They apply equally to every civilization that has ever existed anywhere in the observable universe, and they will continue applying long after every star currently burning has exhausted its fuel and gone dark. The aliens who found the golden record are subject to them exactly as we are. Their level of technological sophistication determines how close they can approach the wall. It does not determine whether the wall exists. The first and deepest layer of the wall is Einstein's special relativity, and it is worth spending real time here, because the popular understanding of what special relativity says is often imprecise in ways that matter enormously for this conversation. Most people understand special relativity as meaning that nothing can travel faster than light, and that is correct, but it understates what the theory actually says, which is something considerably stranger and more absolute. Special relativity does not say that light speed is a limit in the way a speed limit on a road is a limit, a rule imposed from outside that could, in principle, be broken if you were willing to accept the consequences. Special relativity says that the speed of light is a structural feature of space-time itself, woven into the geometry of the universe at the deepest level, and that the reason nothing with mass can reach it is not because reaching it is forbidden, but because reaching it is self-contradictory. As an object with mass accelerates toward light speed, the energy required to continue accelerating does not increase linearly. It increases, according to the Lorentz factor, a mathematical relationship that diverges to infinity as velocity approaches the speed of light. To reach light speed would require infinite energy. Infinite energy does not exist. Therefore, light speed is not a barrier that is hard to cross. It is a barrier that it is physically incoherent to cross, in the same way that it is physically incoherent to have a temperature lower than absolute zero. This is not an engineering problem. It is not a fuel problem. It is a geometry problem. The geometry of space-time is such that light speed is the asymptotic limit of velocity for anything with mass, the boundary that can be approached but never reached, the horizon that recedes as fast as you advance toward it. No amount of additional technology changes this. A civilization a billion years ahead of us technologically still cannot cross this boundary, because a billion years of additional technology does not change the geometry of space-time. It is, to use the word that physicists use when they want to be absolutely precise, a law. Now, here is where it gets interesting for the story of the golden record and the civilization that found it, because the wall is not actually light speed. Light speed is the far edge of the wall. The wall begins considerably closer than that, at speeds that are challenging but not infinitely so, because of the second layer, the rocket equation, and the problem of energy and mass. To understand why this layer matters so much, you have to understand what propulsion actually means. A rocket works by throwing mass out the back. Newton's third law The momentum of the exhaust in one direction equals the momentum gained by the spacecraft in the other. Every rocket that has ever flown, from the smallest sounding rocket to the most powerful launch vehicle humans have ever built, works this way. Chemical rockets, nuclear thermal rockets, ion drives, they all throw mass out the back, and the spacecraft moves forward in response. The efficiency of a rocket is measured by its specific impulse, which is essentially a measure of how much thrust you get per unit of propellant, and this is where the Tsiolkovsky rocket equation becomes devastating for anyone dreaming of interstellar travel. The Tsiolkovsky rocket equation, derived in 1903 and never superseded because it follows directly from conservation of momentum, says that the mass ratio of a rocket, the ratio of its total mass at launch, including all propellant, to its final dry mass, after all propellant is burned, grows exponentially with the velocity you want to achieve, divided by the exhaust velocity of the propellant. That exponential growth is the knife blade. For velocities small compared to exhaust velocity, the equation is manageable. For velocities large compared to exhaust velocity, it becomes catastrophic. And for interstellar travel, the velocities required are enormous compared to the exhaust velocity of any propellant we currently know how to use. Consider what reaching even 1% of the speed of light means. 1% of light speed is approximately 3,000 kilometers per second. The best chemical rocket exhausts we have ever produced achieve exhaust velocities of roughly 4.5 kilometers per second. Using the Tsiolkovsky equation, the mass ratio required to accelerate a spacecraft to 1% of light speed using chemical propulsion is not a large number. It is not a very large number. It is not an astronomically large number in the casual sense of that phrase. It is a number that is larger than the estimated total number of atoms in the observable universe. The mass of propellant required to send even a gram of payload to 1% of light speed using chemical rockets is not a physical quantity. It exceeds the mass of everything that exists. This is not an engineering challenge waiting to be solved with better rockets. It is a mathematical proof that chemical rockets do not belong in the category of technologies that could ever produce interstellar travel, regardless of how much time and investment is applied. Nuclear thermal propulsion does better. A nuclear thermal rocket heats a propellant, typically hydrogen, by passing it through or near a nuclear reactor, achieving exhaust velocities several times higher than chemical rockets, perhaps 2 to 8 kilometers per second in practical designs. This improves the mass ratio requirement substantially, but does not fundamentally change the picture. The required mass ratios for interstellar velocities remain physically impossible using nuclear thermal propulsion. Nuclear pulse propulsion, the concept in which a spacecraft rides a series of controlled nuclear detonations, essentially using nuclear explosions as the exhaust, is more efficient still, and theoretical designs, studied in the 1960s under the name Project Orion, suggested that nuclear pulse propulsion might achieve perhaps 0.1% of the speed of light in optimistic scenarios. That is still a journey time of over 4,000 years to Proxima Centauri. The propellant mass requirements, while physically possible, unlike the chemical case, are still staggering thousands of nuclear devices for a single mission. The only propulsion concept that meaningfully approaches interstellar velocities in theoretical analysis involves either nuclear fusion or antimatter. A fusion rocket, using the most energetically favorable fusion reactions, specifically the fusion of helium-3 with deuterium, could theoretically achieve exhaust velocities of roughly 10% of the speed of light, which would change the mass ratios from impossible to merely extreme. A spacecraft using such a propulsion system to reach Proxima Centauri at perhaps 5% of light speed would require, in conservative estimates, a mass of fusion fuel many times greater than the dry mass of the spacecraft. Challenging, but physically coherent. The problem is that we do not know how to build a practical fusion rocket. Despite decades of research, controlled nuclear fusion that produces more energy than it consumes has only recently crossed the threshold in laboratory conditions, and the path from laboratory fusion to a working spacecraft propulsion system involves engineering challenges that are genuinely enormous rather than merely marketing department enormous. Antimatter is the theoretical upper bound. When matter and antimatter meet, they annihilate completely, converting all of their mass to energy at 100% efficiency, the maximum that Einstein's famous equation relating energy to mass allows. There is no more efficient energy source in known physics. An antimatter rocket would be, in principle, capable of achieving a substantial fraction of light speed with a manageable propellant mass ratio compared to the impossible requirements of less energetic propulsion methods. An antimatter engine producing exhaust at nearly light speed could theoretically achieve mass ratios on the order of a few to one for velocities of tens of percent of light speed. These are still challenging numbers, but they are physically possible numbers. The problem with antimatter is that we produce it one particle at a time in particle accelerators. The world's most powerful particle accelerators combined produce perhaps a few billionths of a gram of antiprotons per year. To fuel an interstellar mission would require grams or kilograms of antimatter. At current production rates, producing 1 gram of antiprotons would take longer than the current age of the universe. And antimatter must be stored in magnetic containment fields that require continuous power because antimatter annihilates anything it physically contacts, including the walls of any container made of ordinary matter. The storage problem alone is a technological challenge at a level that makes the engineering of, say, a nuclear reactor look trivially simple. Now, and this is important, we are talking about what we can do. The civilization that found the golden record is not us. They may be thousands of years ahead of us technologically. They may have solved fusion propulsion in a practical way. They may have found a method of antimatter production or storage that we have not conceived. They may have a physics framework that we do not yet have, built on observations we have not yet made, that opens propulsion possibilities we cannot currently calculate. It would be wrong to say that because we cannot build an interstellar spacecraft today, no civilization can. That would be the same kind of parochial thinking that led people in the 19th century to argue that heavier-than-air flight was theoretically impossible. But here is what does not change regardless of technological advancement. Here is what remains the wall regardless of how advanced the civilization is. Even with perfect antimatter propulsion, a technology that extracts the maximum energy physically available from mass, the journey times and energy costs of interstellar travel remain formidable in ways that do not simply vanish with more engineering. A round trip from a star, 100 light-years away, traveling at 90% of light speed, requires roughly 220 years in Earth time and roughly 95 years in ship time, thanks to time dilation. 100 years for the travelers, subjectively, and when they return, more than 220 years have passed at home. Everyone they knew is dead. The civilization that sent them has changed in ways that, over 2 centuries, could be profound. Languages drift, governments change, technologies advance, priorities shift. The mission that seemed urgent when it launched may have been rendered irrelevant by the simple passage of time. This is not a solvable problem with better engineering. It is a consequence of special relativity that cannot be designed around. The time dilation that makes the journey subjectively shorter for the travelers is the same effect that makes the interval longer for everyone who stayed behind. You cannot have one without the other. A civilization that sends interstellar missions is a civilization that accepts the permanent rupture of the social thread connecting the travelers to their home, not because the technology fails, but because the physics demands it, and the energy. Even with antimatter propulsion at near light speed, the energy required to accelerate a crewed spacecraft is enormous by any standard, except that of a civilization that has learned to harvest stellar energy directly. The kinetic energy of a 1,000-ton spacecraft, a modest size for something carrying the life support systems and supplies needed for a journey of many decades at 90% of light speed, is approximately 2 × 10⁻⁴ power joules. That is more than the total energy output of the Sun over a period of roughly 3 hours for one spacecraft, one way. The deceleration at the destination requires an equal energy expenditure. The spacecraft must slow down from near light speed to something manageable, and if it is carrying its own propellant for deceleration, the Tsiolkovsky equation demands that the initial propellant mass be multiplied accordingly. The round trip, including deceleration at the destination and acceleration for the return, roughly quadruples the energy requirement. And all of this propellant must be accelerated along with the payload, which demands more propellant to accelerate the propellant, which demands more propellant still, in the spiraling recursion that makes the rocket equation so merciless. Nikolai Kardashev, the Soviet astronomer who in 1964 proposed the classification system that bears his name for the energy use capacity of civilizations, imagined 3 types. A Type 1 civilization controls the energy resources of an entire planet. A Type 2 civilization controls the energy resources of a star. A Type 3 civilization controls the energy of an entire galaxy. By Kardashev's rough estimates, we are currently a Type 0 civilization. We do not yet fully control even our own planet's energy resources. A Type 2 civilization, one that has learned to capture and direct the entire energy output of its star, would have access to approximately 4 × 10⁻26 power watts continuously. For such a civilization, the energy cost of a single interstellar mission, while still significant, becomes conceivable as a civilizational project rather than an impossible fantasy. They have the energy. They have only to solve the engineering. But the biology does not care about the engineering. Biology is the third layer of the wall, and it is in some ways the most insidious, because it is the one that advances in technology have the most difficulty addressing. The organisms that evolved on a planetary surface evolved there because planetary surfaces are physically manageable environments for biology. Gravity pulls consistently in one direction and prevents bodily fluids from pooling in the wrong places. A planetary magnetic field deflects much of the high-energy particle radiation from space. A planetary atmosphere provides the chemical inputs biology needs and filters out wavelengths of electromagnetic radiation that would damage cellular machinery. The biological systems that work on a planetary surface were not designed for the interstellar medium, and they show it clearly whenever we try to operate them there. Consider what happens to a human body in microgravity. The cardiovascular system, which evolved to pump blood vertically against a constant downward pull, redistributes fluid toward the head when that pull disappears. This causes facial puffiness, nasal congestion, and, more seriously, increases intracranial pressure in ways that compress the optic nerve and alter the shape of the eyeball, causing vision problems that persist even after return to gravity. Astronauts who have spent 6 months on the International Space Station, which orbits inside Earth's magnetic field and is therefore partially shielded from the most energetic space radiation, have returned with measurable reductions in visual acuity that, in some cases, did not fully reverse. Bone density decreases at roughly 1 to 2% per month in microgravity because the mechanical loading that bones require to maintain their density disappears when there is no gravity to push against. Muscle mass atrophies. The structure of the spine changes as the intervertebral discs expand without compression. The immune system is altered. The gut microbiome shifts. After 6 months in low Earth orbit, astronauts typically require months of recovery and rehabilitation to return to full function on Earth's surface. Now, scale that to an interstellar journey. Even at 90% of light speed, the subjective journey time from a star 100 light-years away is roughly 48 years. 48 years in microgravity, if that is what the ship provides, would produce physiological changes that go far beyond what any rehabilitation program could address. Bone density does not simply diminish, it eventually compromises the structural integrity of the skeleton. Muscle atrophy, over decades, reaches a point that no exercise regime on board can prevent without gravity to work against. The circulatory and neurological changes would compound over decades in ways that medical science, even advanced medical science, would struggle to reverse, because the body would have reorganized itself around a new equilibrium point, suited to the ship environment and completely incompatible with any planetary surface. Rotating sections of the ship can simulate gravity centrifugally. This is a real and theoretically viable solution, and any advanced civilization contemplating interstellar travel would almost certainly implement it. But even artificial gravity through rotation does not solve the radiation problem, and radiation is where the biology gets genuinely dangerous rather than merely inconvenient. Cosmic rays are high-energy particles, primarily protons, and atomic nuclei accelerated to near light speed by supernova shockwaves, active galactic nuclei, and other extreme astrophysical processes, and they pervade the galaxy continuously. Inside the solar system, the Sun's magnetic field and the geomagnetic field of Earth together provide significant shielding. In interstellar space, there is no such protection. The galactic cosmic ray flux is roughly 4 times higher than what astronauts experience in low Earth orbit. These particles carry enough energy to penetrate meters of solid shielding. The most energetic cosmic rays can pass through several meters of water, which is among the most effective shielding materials per unit mass available, without stopping. They create cascades of secondary particles in whatever material they pass through, and those secondary particles deposit ionizing radiation in biological tissue, damaging DNA, disrupting cellular repair mechanisms, and increasing the risk of cancer and neurological damage. For a journey of decades, the cumulative radiation dose from cosmic rays, even with substantial shielding, would likely exceed safe limits by factors that no medical countermeasure currently proposed could fully address. Adding more shielding adds more mass, which demands more propellant, to accelerate that propellant in the same recursive spiral that makes the rocket equation so demanding. There is a practical limit to how much shielding any spacecraft can carry, and that limit is determined by the rocket equation as much as by materials science. At relativistic velocities, the problem becomes even more acute. At 90% of light speed, the interstellar medium, those 1 atom per cubic centimeter of hydrogen and helium that Part 2 described, does not behave like the negligible nothing it is at low speeds. At relativistic velocity, even individual hydrogen atoms become radiation hazards. The kinetic energy of a hydrogen atom at 90% of light speed in the reference frame of the spacecraft is roughly equivalent to that of a low-energy cosmic ray. The interstellar medium becomes, effectively, a continuous radiation bath proportional to the square of the velocity. At high enough fractions of light speed, the interstellar medium alone, those rare, sparse atoms, delivers a radiation dose that would be lethal without shielding, that adds mass in quantities that again challenge the rocket equation. This is a physical constraint that cannot be engineered away, only managed, and the management cost is always paid in mass. Now here is something that is rarely discussed in conversations about interstellar travel and is genuinely important. The alien civilization that found the golden record faces all of these same constraints, not because they are limited in the way we are limited, but because these constraints do not arise from the limits of engineering. They arise from physics that is the same everywhere. Whatever they are made of biologically, if they evolved on a planetary surface which any life-bearing planet would produce by definition, because life arises from the chemistry of solid surfaces and liquid environments, their biology was shaped by the conditions of that surface, not by the conditions of interstellar space. Their bodies, or whatever structures their biology uses, would face some version of the gravity, radiation, and time problems that our bodies face, because those problems are functions of physics, not of human specificity. Their propulsion technology may be vastly superior to ours. They may have mastered fusion or antimatter, or some method we have not conceived. But the energy they need to move a crude vessel to a significant fraction of light speed is determined by the laws of thermodynamics and relativity, not by their engineering level. The time dilation that separates travelers from their home civilization is determined by special relativity, not by their engineering level. The radiation environment of the interstellar medium at relativistic velocity is determined by the physics of particle interactions, not by their engineering level. They can approach the wall closer than we can. A sufficiently advanced civilization might be able to touch the wall to build spacecraft that travel at 90 or 95 or 98% of light speed, accepting all the costs that involves. But they cannot go through the wall. There is one class of proposed solutions that deserves serious attention before we close the door entirely. And that is the class of solutions that involve bending space rather than crossing it. Proposals such as the Alcubierre warp drive, which is a solution to the equations of general relativity first described by physicist Miguel Alcubierre in 1994, that would, in principle, allow a spacecraft to reach distant destinations faster than light, without locally violating special relativity. The idea is elegant. Instead of the spacecraft moving through space at superluminal velocity, space itself contracts ahead of the spacecraft and expands behind it, carrying the spacecraft along like a surfer on a wave. The spacecraft itself never locally exceeds light speed relative to the spacetime around it. It is the spacetime that moves, and spacetime is not subject to the mass infinity problem that afflicts material objects. The problem, and it is not a small problem, is that the Alcubierre drive requires a form of energy density that is negative. Negative energy density is not simply energy with a minus sign. It is a condition in which the energy density of a region of space is less than the energy density of a complete vacuum, less than nothing in the usual sense. This is permitted by quantum field theory in certain limited circumstances, involving phenomena like the Casimir effect, but producing it in the quantities required for a practical warp drive would require either exotic matter with properties that have never been observed and may not exist in nature, or a level of energy manipulation that scales to something approaching the total mass energy content of a planet or more. Every serious calculation of what the Alcubierre drive would require in practice has returned numbers that are, in the current state of physics, not merely impractical, but physically incoherent. They require conditions that may not be realizable in this universe. Regardless of how much energy you have available, wormholes face a similar fundamental problem. A traversable wormhole, a tunnel through space-time, connecting two distant points, is permitted by the equations of general relativity in the same formal sense that the Alcubierre drive is permitted. The equations allow the solution, but the solution requires exotic matter with negative energy density to keep the tunnel from collapsing, and the quantities required are again physically extreme. Wormholes that form naturally would pinch shut too quickly for anything to pass through. Holding one open requires sustained exotic matter conditions that we have no mechanism for producing. These are not engineering problems in the sense that fusion propulsion is an engineering problem. They may be fundamental impossibilities rather than technical challenges, and the honest assessment of the physics is that we do not know, and we cannot know without a level of understanding of quantum gravity that we do not currently possess. So where does this leave the civilization that found the record? It leaves them exactly where it leaves us, capable of reaching the stars, in principle, but not cheaply, not quickly, not without civilizational commitment, not without biological cost, and not within any time frame that would make a response to finding the record feel like a timely or practical reaction in the way that, say, receiving a radio signal and sending a radio signal back would feel. They can imagine crossing the distance to Earth. They can calculate what it would cost. They can understand, as we understand, that the journey is technically possible within the constraints of known physics for a civilization with vastly more energy than we have. And then they must weigh what finding us is worth. Here is an uncomfortable comparison that the physics quietly forces us to make. We are, right now, in a position almost exactly analogous to the civilization that found the record. We have received, in a sense, a message from the universe. The universe itself tells us, through its structure and through our own scientific understanding, that there are almost certainly other civilizations somewhere in the galaxy. The Drake equation, the sheer number of stars and planets, the detection of amino acids in meteorites and complex organic chemistry in interstellar clouds, all of this tells us that we are probably not alone. We know, in principle, where to look. We have instruments that could detect certain kinds of signals, and we cannot go there. We cannot send a crewed mission to the nearest star. We cannot respond in physical form to the knowledge that other beings almost certainly exist. We can only listen and transmit and wait, and exactly what the record does reach. The physics treats everyone equally. The wall stands for us. The wall stands for them. The silence that surrounds the golden record is not the silence of an empty universe. It may be the silence of a universe full of civilizations that have all decoded each other's messages, understood each other's addresses, and looked at the physics and recognized, each of them separately and together, that visiting is something the universe was not designed to make easy. That recognition that the barriers to physical meeting are structural rather than merely technical has a name in the scientific literature. It is one of the proposed resolutions to the Fermi paradox, the famous observation attributed to physicist Enrico Fermi that the universe is old enough and large enough and likely populated enough that we should, by naive statistical reasoning, have detected evidence of other civilizations long ago, and yet we have not. The resolution proposed by this line of thinking is not that other civilizations do not exist. It is that the physics of interstellar travel is hard enough and the galaxy large enough that even a universe full of curious, intelligent, technologically capable species may produce very little actual interstellar travel, in the same way that a world full of curious, intelligent people produces very little personal travel to the most remote and inaccessible places on Earth, not because people don't want to go, but because the cost and the difficulty and the disruption to the traveler's life make it a rare choice rather than a common one. Scaled up to interstellar distances, rare means almost never. Scaled up to the lifetime of the galaxy, almost never means a silence that looks very much like the one we observe. The golden record drifts through that silence at 38,000 miles per hour, carrying its encoded message of a species that reached anyway, knowing the physics, accepting the physics, and choosing to reach anyway. And in that choice, in that act of building something beautiful and launching it into a void that no one expected it to cross, something interesting happens. Something that takes the whole story of physics and propulsion and the rocket equation and the radiation problem and the time dilation and the wall that cannot be crossed and turns it inside out. Something that asks whether the wall is actually the most important part of this story, or whether the reaching itself is the story and the wall is only the context that makes the reaching meaningful. That is where we go next, and it is not a small place. Let us begin with a fact that is easy to state and surprisingly difficult to fully absorb. The golden record is almost certainly the most durable object our civilization has ever made. Not the most powerful, not the most complex, not the most expensive or the most technologically sophisticated, the most durable. In terms of how long it will exist in a recognizable form, the golden record, a 12-inch disc of gold-plated copper in an aluminum jacket, moving through the interstellar medium at 38,000 miles per hour, will outlast virtually everything else humanity has ever produced by margins that are not close. The pyramids of Egypt have stood for roughly 4,500 years. They are already showing significant erosion from wind, sand, and human contact, and in another 10,000 years, absent preservation efforts, they will be substantially diminished. The longest-lasting human artifacts on Earth, certain stone tools, certain cave paintings in protected environments, extend the timeline to perhaps 40,000 years. The Voyager spacecraft themselves, including their structural components, are expected to remain physically intact in the interstellar medium for billions of years because the interstellar medium is extraordinarily benign. For metal objects, no oxygen to cause oxidation, no liquid water, no biological activity, no wind or erosion. The main threat is cosmic ray bombardment, which will slowly alter the crystal structure of the metals over geological timescales. But the gold plating of the record is specifically resistant to this kind of degradation, and the grooves of the record, physically carved features in the metal, will remain readable by a stylus long after more fragile structures have been compromised. Estimates vary, but conservative scientific opinion places the duration of the record's legibility at something between 100 million and 1 billion years. 100 million years is longer than the entire evolutionary history of modern mammals. 1 billion years is roughly 1/5 of the current age of the universe. During that span, the Sun will have completed approximately 4 full orbits of the Milky Way galaxy. During that span, the continents of Earth will have drifted into configurations that would be unrecognizable from any current map. During that span, the species Homo sapiens will almost certainly have either evolved into something so different from us that the word human no longer meaningfully applies, or cease to exist entirely, or both in sequence. During that span, our civilization, the civilization that built libraries and cathedrals and particle accelerators and interstellar spacecraft, will be as distant in time from whatever intelligence exists on Earth then as the first bacterium is from us now, and the record will still be moving at 38,000 miles per hour through the dark. This is the first genuinely new thing that Part 4 asks you to sit with. Not the distance, not the physics, not the probability of contact. The duration, the sheer, vertiginous span of time during which the record will continue to exist and to carry its information, drifting through the galaxy in silence, completely unmonitored, completely unanswered, completely alone. The people who made it are all dead now, or will be soon. The organization that made it possible is still operating, but the mission it launched has effectively ended. The engineers who coaxed signals from a spacecraft more than 25 billion kilometers away and nursed its failing power systems through decades of operation are retiring or have retired. The spacecraft will go silent, and the record will keep moving. There is something in this duration that changes the meaning of everything that came before in this story. The physics of the wall, the rocket equation, the energy problem, the biological limits, the time dilation, all of it was framed as a discussion of what any civilization, including the one that found the record, cannot easily do. But the duration reframes the question. The question is not simply, can they come? The question is, what is the time scale on which anything happens here? And on the time scale of the record's existence, the physics of the wall looks different. Not more permissive, the equations do not change, but differently significant. On a time scale of 100 million years, a civilization that is currently 1,000 years behind us technologically catches up and surpasses us and potentially solves the problems we cannot solve. On a time scale of 100 million years, a civilization that currently exists at the Type II Kardashev level, controlling the energy of its star, has had time to expand its capabilities in ways that are genuinely difficult to predict. On a timescale of 100 million years, the proposition that no one will ever come to look at the planet that made the record becomes less a statement about physics and more a statement about probability across an enormous range of future possibilities that we cannot enumerate. But here is what makes the golden record philosophically extraordinary, and this is the genuinely new angle that Part 4 brings to a story that has already covered physics and probability and propulsion in exhaustive detail. The record was not made to be found. Not really. It was made to be sent. This distinction sounds semantic, and it is not. A message designed to be found is optimized for findability. It is loud, it is bright, it is directional, it is persistent. A radio beacon designed to be detected would broadcast continuously on frequencies known to be monitored. A spacecraft designed to be encountered would be reflective, would carry active transponders, would be sent on a trajectory calculated to pass through inhabited regions. The golden record is none of these things. The spacecraft it travels on was not aimed at any star. It broadcasts no signal. It is not reflective enough to detect from stellar distances. It was launched at a speed that virtually guarantees it will not encounter any other star system for tens of thousands of years, and even then will pass at distances measured in light years, which are not close. Carl Sagan and his committee knew all of this. They designed the record anyway. They optimized it for longevity and for informativeness, not for discoverability. Why? Because sending the message was the point, not the receiving, the act of sending. This is a distinction that cuts across the entire history of human communication, and it carries weight that the physics and the propulsion and the probability calculations do not fully capture. Humans have always made objects and sent them into durations and distances where response was not expected. We paint on cave walls, not because we expect the paintings to be seen by anyone in particular, but because the act of marking the wall says, "I was here, I saw this. This mattered enough to record." We write in journals that we know no one may read. We bury time capsules that may never be dug up. We write music that we know will outlast us and hope it continues to be played, but do not require it as a condition of writing. The act of making something and giving it to time, releasing it from the moment of its creation into whatever future will hold it, is one of the most consistent behaviors across human cultures, across all of recorded history. The golden record is the largest and most permanent version of this impulse that our species has ever produced. It is a cave painting traveling at 38,000 miles per hour. It is a journal entry launched into eternity. It is a message in the most literal possible sense, not a communication designed to receive a reply, but a communication designed to carry something true about the sender into a future the sender will never see. This reframing matters for how we understand what the record says about us as a species, independent of any question about whether anyone will find it. The record says that we are a species that values the act of reaching over the certainty of being received. It says that we understand we are small and brief, and that the universe is vast and old, and that this understanding does not reduce us to silence. It says that we looked at the physics, at the wall, at the rocket equation, at the biological limits, at the 40,000-year drift toward Gliese 445, and we made something anyway, not despite the physics, exactly, but with the physics fully in view. We made something that does not pretend. The wall is not there. We made something that accepts the wall and reaches across it anyway in the only form that the physics permits. Information, encoded in metal, moving through the dark at the speed of a spacecraft rather than the speed of light, on a journey measured in geological time. There is a sentence written on the record that carries more weight the longer you think about it. It is from President Jimmy Carter's message. We are attempting to survive our time so we may live into yours. The phrase, your time, is addressed to whoever finds the record, whenever they find it. But look at what it actually says. It does not say, we will be there when you find this. It does not say, we expect to hear from you. It says, we are trying to survive, acknowledging the uncertainty of survival, the precariousness of a technological civilization that has existed for less than a century and is navigating extraordinary challenges. And it says We hope that something of us will persist long enough to reach forward in time, into a future that is explicitly not ours, but theirs, the finders. It is one of the most honest and humble statements any civilization has ever made about itself, because it does not claim permanence. It claims aspiration. The record carries something else that has not been fully examined yet in this story, which is what it reveals about humanity through what it chose to include and what it chose to leave out. The committee that assembled the record was acutely aware that they were making choices that would represent the entire species to an audience that could not ask follow-up questions. They debated extensively what to include. They chose not to include images of war, of violence, of suffering, of environmental destruction, not because they wanted to deceive, but because they made a conscious decision that a first impression should lead with the best of what we are rather than the worst. They included music of extraordinary variety. They included the sounds of nature with deliberate attention to non-human life. They included the structure of DNA, but not images of disease. They included children, but not conflict. This was a curatorial act, and curation is itself deeply revealing about a species. The decision to curate rather than document without filter reveals that we have values about how we wish to be seen, that we understand the concept of a first impression, that we are capable of the kind of self-aware perspective-taking that says, what would we look like to someone who had never encountered us and had no context for our history? We assembled a portrait, not a complete one, not an honest documentation of everything, a chosen portrait. And the fact that we were capable of choosing, of looking at ourselves from the outside and selecting what to show, says something about the kind of minds that made the record, something that the record itself communicates, indirectly but unmistakably. Andrew Yan, reflecting on the record decades after its creation, described it as a way of saying, we are here, we are alive, we feel, we think, we make music. That compression is important. We feel comes before we think. For the people who made the record, the emotional content, the music, the whale song, the brainwaves, the laughter was not supplementary to the scientific content. It was not decoration appended to the serious material of DNA diagrams and pulsar maps. It was core. It was, in the committee's understanding, one of the most important things to communicate, because any sufficiently advanced civilization will have mathematics and physics. Those are not achievements that distinguish species, because the laws of physics are the same everywhere, and any civilization old enough to be doing interstellar science will have discovered them. What distinguishes species is what they do with their intelligence beyond survival, what they make when they are not strictly required to make anything, what they play when they could be doing something useful. The music and the whale song and the brain waves of a woman in love are not the icing on the golden record. They are its truest content. This brings us to the final and most important reframing of the entire story. We began this documentary asking what would happen if aliens found Voyager 1, a question about them, about their capabilities, about their decisions. We spent Part 3 establishing that the physics makes physical visitation enormously difficult, regardless of technological level, that the wall is real and the wall stands for everyone. And now, in Part 4, having laid out both the physics and the meaning, the question changes. The honest conclusion, the one that the entire journey of this story has been building toward, is not about them at all. It never really was. The golden record is a statement about us, about what kind of species reaches into a void it cannot cross, makes something beautiful, and lets it go. The Voyager record will almost certainly never be found. The physics of interstellar space, the vastness of the distances, the near invisibility of the spacecraft, the geological timescales involved, all of it conspires against finding. Carl Sagan knew this. Frank Drake knew this. Anne Druyan knew this when she sat in that chair and let her brainwaves be recorded for 1 hour while she thought about the history of the world and drifted into thinking about love. They sent the record anyway, and in sending it, they did something that the physics could not prevent and cannot undo. They made the act of reaching permanent. The record cannot be unreached. Whatever happens next, whether it drifts through the galaxy for 1 billion years in total silence, or whether some civilization somewhere in the unimaginable future finds it and decodes it, and hears the humpback whales, and looks at the pulsar map and understands where we were, the reaching has happened. The beautiful, futile, entirely human, entirely characteristic reaching has happened, and it is encoded in gold, and it is moving through the dark right now at 38,000 miles per hour. And it will be moving when every institution that exists on Earth today has dissolved into history, and it will be moving when the history itself is lost, and it will still be moving. There is a particular quality to things made with full awareness of their own likely futility. It shows up in letters written in wartime to addresses the writer does not know are still valid. It shows up in scientific papers written by researchers who do not expect to live to see their ideas confirmed or refuted. It shows up in trees planted by old people who will not live to sit in their shade. The quality is not quite hope, and not quite resignation, and not quite defiance. It is something closer to a clear-eyed acceptance of the terms the universe offers, combined with the refusal to let those terms be the last word on what a mind capable of understanding them might choose to do. We understand the wall. We know the equations. We know the distances and the time scales and the vanishing probability of contact. And we built the record, and we engraved it, and we bolted it to the spacecraft, and we launched it on a gravity assist trajectory that used Jupiter and Saturn as slingshots, and we tracked it for nearly 50 years across 25 billion kilometers, and we listened to it until the listening became technically impossible, and now we let it go. That letting go is the most honest thing the record says about us. Not the mathematics, not the pulsar map, not the music or the whale song or the structure of DNA. The act of launching something into a duration and a distance where we cannot follow it, cannot maintain it, cannot correct any errors in it, cannot update it to reflect what we have since learned or become, and doing that deliberately, with full understanding, is the statement. It is the statement that we know we are temporary and we choose to make things that might not be. It is the statement that we value communication across distances too great for communication to be practical. It is the statement that we are the kind of species that cannot look at the night sky without wanting to reach it, even knowing that wanting and reaching are not the same thing as arriving. The universe enforces the wall. The universe is indifferent to the reaching. The physics does not care that we sent the record. The interstellar medium does not make room for it. The distances do not shrink. The equations do not bend. And none of that changes what was done, or what it means, or the fact that somewhere between the stars right now, moving at 38,000 miles per hour, through a silence so deep that human language does not have adequate words for it, there is a gold-plated copper disc containing the sound of thunder and the song of humpback whales and Bork's Brandenburg Concerto Number 2, and the brainwaves of a woman in love, and a map that says, here. This is where we were. We were small. We were brief. We were afraid of the dark, and we reached into it anyway. And the record keeps going. Float gently, little Voyager. Through the quiet between the stars, the universe is vast, and you have all the time there is.